Okay, we're going to look at how to find area between two polar curves. This is based on the calculus lecture I gave. And in this particular lecture, we talked about how to determine area within a polar curve. Now, this one is saying to determine the area that lies, here's going to be the key phrase here, inside both polar curves. So we want the area that's going to be inside both curves here. So the area here that's going to be inside both curves, we have two polar curves here. We're talking about this particular region there. And what I would suggest is to use properties of symmetry here. That whatever that area is here, we're going to find that. And in fact, we might be able to do even better. If we take a closer look, if we find this particular area, whatever that area is, you can call this area A. The area is going to be 4 times that because we have, by symmetry, we have this same value for area, and this same value for the area, and this same value for the area as well. So we have some symmetric properties that we're going to use. So the key would be here, really, to find this area. If you go back and try to recreate everything before it crashed, essentially take this area in red here and multiply it by 4. So whatever this area is going to be, that's going to be area inside both the curves here. So we're going to multiply that whole area by 4 here. So whatever that value is. So I'm going to just go back and highlight that for you guys. Sorry for the crash. And that's going to be here. Our real area is going to be, satisfy this equation here. A equals 4 times that, whatever that shape will be. We'll say A sub 1. Okay? And this is that A sub 1, I guess. So 4 times that to get all the others. And that's area inside both curves. Now, the reason I think that that's going to be a great approach for us is because we're going to have to use now to find that area. Let's get rid of some of these things. The particular angle here is 0 and pi over 2. I guess it doesn't like that, so we're going to use this particular. There we go. So my theta here, the angles, be theta is 0 and theta is pi over 2. So that's going to be what we use here to determine that area, that little sliver. We're going to just multiply it by 4. So remember what we did here. We have to know now, if I draw another, let's use this black here, another arrow for some theta now, to find the area. If we take that closer look, we have to find, we're going to use what's called the blue curve. So that blue curve is what we use. We have to know what curve is that in blue. So I got 2 curves here. R equals 1 plus cosine theta and R equals 1 minus cosine theta. So I want to remind you in Desmos here, we got the picture I got was from this picture and this picture. So these are the things we talked about and looked at. So it looks like the blue curve is r equals 1 minus cosine theta. It's the cardioid. So I'm going to use that curve here. Okay, so if you can see that this blue curve now is going to be that A1 area. It's going to be the integral from 0 to pi over 2, 1/2 r squared d theta. So we're just really finding this area right in here. Okay, so if this is in the way, maybe I'll just draw this picture. And as you can see, we're hitting the blue curve from 0 to pi over 2. We're not even touching the black curve at all, just the blue curve. So it's not really area between two curves in some sense. And these locations, again, 0, pi over 2 for theta. So it's pretty simple. We need to know the blue curve. You know, the blue curve in this picture here was going to be the 1 minus cosine theta. All right, remember from Desmos here, the blue curve. 1 minus cosine theta. So A1 will be integral 0, pi over 2, 1/2, 1 minus cosine theta to the second power d theta. Which is 1/2, 0, pi over 2, 1 minus 2 cosine theta plus cosine squared theta if I use FOIL. And this is A1. But that means that A will be, since A1 is here, I guess we should say that's that blue portion. The total area is 4 times that. So multiply 4 times A1, and you're going to get 4 times 1/2, or the area is going to be 2. 0 pi over 2, 1 minus 2 cosine theta. Plus the cosine squared theta. Okay, now remember what we do with this portion here. Cosine squared theta, we're going to use a half angle identity. 1 minus cosine 2 theta. So we get 2, 0, pi over 2, 1 minus 2 cosine theta, plus 1/2 minus 1/2 cosine 2 theta d theta if we distribute there. So 2, 0 to pi over 2. 1/2 plus 1 is 3/2. So I get 3/2 minus 2 cosine theta minus 1/2 cosine 2 theta, and this will be d theta. Okay, well, let's try to see if we can integrate here. 2, 3/2 theta. Now the derivative of sine is cosine, so it'll be minus 2 sine theta. And over here, you're going to have to use u sub. And that's going to be now, if I already have a factor of 1/2, 1/4 sine 2 theta, from 0 to pi over 2. Okay. Now, if I use distributive property here, this will be 3 theta minus 4 sine theta minus 1/2 sine 2 theta from 0 pi over 2. I just distributed here the 2. So we get 3 pi over 2 minus 4 sine pi over 2 minus 1/2 sine 2 times pi over 2 minus 3 times 0 minus 4 sine 0 minus 1/2 sine 2 times 0. So these are all zeros here. And then sine of 90 degrees is 1, and 2 times pi over 2 is pi, so sine of pi, well, that's 0. So your final answer is going to be 3/2 pi minus 4 times 1, which is 4. So it's 3/2 pi minus 4. And this is actually, again, this is the area here. So, ladies and gentlemen, there you go. This is all the work you'd have here. So the area inside both curves really turns out to be, find the area in quadrant 1 for the cardioid represented by r equals 1 minus cosine theta. So you have two cardioids here. And there you go. So that's the first one. Area between two polar curves. Area that lies inside both. So that's what we're going to do. We're going to go through these problems here and find the area that lies inside both curves here. So in this situation here, we have two two-leaf roses. And to find the area inside both of these curves, they're talking about this area right here. Now, instead of using the big, I should say the big highlighter in red that I did here, I'm not going to use the big highlighter. This is going to be, I'm going to try to take a look at how this looks here for us. I'm going to draw this picture. Here and here. So I'm going to use the same idea as I did in the past here. We're going to use symmetry. So area really inside both curves is what you see here, because there's a portion of the curves down there too. So my area here is going to be, if I want to describe it again this way, 4 times A1, where by symmetry, this is that A1 area. So I know here, since this is a horizontal line, theta will be 0. The question is, what is theta here now? We need that point of intersection. And we have to know what kind of rose this is, because again, it's going to be the green curve that we use if we do use this approach. Meaning if we take the area of that little sliver in red here, we just multiply it by 4 because this is symmetric, and we should find out what this area is. It's with the green curve. But we need here this theta. So this is what we're going to get first. We're going to get that theta here. Now, how you find theta is by finding the points of intersection. You're going to take both curves here. R squared is sine 2 theta. R squared is cosine 2 theta. So you set the curves equal to each other, meaning R squared will equal R squared, which means sine 2 theta will equal cosine 2 theta. And divide both sides by cosine 2 theta. We'll get tangent 2 theta is 1. If you like, you could do a substitution. You say let x be 2 theta. And so you need to know where tangent x is 1, and that happens in two locations. X is pi over 4, or X is going to be the opposite side. Okay, pi over 4, 2 pi over 4. Looks like it'll be pi over 4, 1, 2, 3, 4. That's 5 pi over 4. So if you remember this. But this is 2 theta here. So 2 theta will be pi over 4, which means theta would be pi over 8. Now we don't need the other angle. This is that angle that we're looking for, pi over 8. And that's what we have up here. This is the pi over 8 angle. So I just need that pi over 8. So now I know the point of intersection here for this curve. We do have another point of intersection, but you say, how would I get that? You don't need it, but 2 pi is 5 pi over 4, or 2 theta. That means theta will be 5 pi over 8. So I just want to point out that this angle over here will be 5 pi over 8, but we do not need it. Don't need it. This would be that 5 pi over 8. So we're just going to take what we need. We're going to take that 4 times that area again. We're going to do it the same way, and we need to know the area in green. And remember, in Desmos, these are really the green area here. It was really r squared, which is sine 2 theta. That's the green one that we had earlier. R squared is sine 2 theta. So that green area is what we're going to use. So here's the formula. That area will be 1/2 the integral from 0 to pi over 8 r squared d theta. But it's the green area here because if I take a look now, draw my arbitrary theta, you hit the green curve. So you're hitting that green curve. And that's r squared right up here, sine 2 theta. And the other one is going to be the black curve, but we don't need it for this question. So it's that green area there. And r squared is sine 2 theta. Now that's kind of interesting because we already have the r squared. We just replace that with sine 2 theta. So this integral becomes 1/2, and this is a1, by the way, from 0 pi over 8 sine 2 theta d theta. And since area is 4 times a1, then the area will be 4 times that 1/2. 0 pi over 8 sine 2 theta d theta, or the area is 2, 0 pi over 8 sine 2 theta d theta. So we're going to integrate by u sub. U sub gives us, this is going to be now, if we integrate 2, remember u sub, u will be 2 theta. So we're going to get minus 1/2 cosine 2 theta from 0 to pi over 8. Which will give you minus cosine 2 theta from 0 to pi over 8. So when we apply our limits, we get minus cosine 2 times pi over 8 plus cosine 2 times 0. So minus cosine pi over 4 plus cosine of 0. Now, cosine of 0 here is the value 1. Cosine of pi over 4 is 1 over the square root of 2, or 2 square root of 2. And don't forget, you have a minus sign already. So we get minus square root of 2 over 2 plus 1, or we can say 1 minus the square root of 2 over 2, if we rationalize the denominator here. And there you go, ladies and gentlemen. That's how you find area between two curves here. So you can use some properties of symmetry here. You're just hitting that green curve. So we're going to look now at the area between two curves here, and then this is a circle here. You got two circles. So the area now here that they're talking about between these two curves is what you see here. So finding the points of intersection again, here and here, so that we could use symmetry, finding that angle. We know this is theta equals 0. We have to find what this theta is. We don't know what it is. But if we only get this area here and we double it, we'll find, because of symmetry, we'll find the area that's inside both curves. So I also need to know what circle is represented in black here. And those are some things that we have to find out. So let's write down what we need to get area within both curves. In this case, area will be double A1. And this red portion, this sliver, is A1. So let's find the points of intersection. We do that by setting the curves equal to each other. So R is 2 sine theta, and R is 2 cosine theta. We set them equal. So if we say R is R, that means 2 sine theta is the same as 2 cosine theta, which means sine equals cosine. Divide both sides by cosine, and again, you end up with the equation tangent theta is 1, and we know theta will be pi over 4. So this angle is simply pi over 4. And that's what we were looking for, pi over 4. This is the 0 angle. Okay, so we need to know again, or how we set this up, would be that area. Area will be 2 times A1, where A1 will be the integral from 0 to pi over 4, 1/2 r squared d theta. We just need to know which circle we have in that black curve. Now, remember what we did. We know all these curves already in Desmos. This is where we got that picture. So the black curve is actually 2 sine theta. So this is where we got the pair. So it's 2 sine theta. So I replace R here with 2 sine theta, because that's the black curve there. So again, even though they say find area inside both curves, if I do it strategically this way, I'm going to get my answer. Let's see what happens now all together here. So let's pull out some constants. 2 times 1/2, 0, pi over 4, and I take 2 sine theta and I square that, d theta. So 2 times 1/2 is 1. And I'm going to get the integral from 0 to pi over 4 for sine squared theta d theta. So I can pull out my, well, I'm going to leave it this way for now. We're going to use our power reducing formula. This becomes 1/2 times 1 minus cosine double theta. And that replaces my sine squared theta here. So 4 times 1/2 will give me 2. So 4 times 1/2, I get 2 now. 1 minus cosine double theta d theta. 2. 1 minus cosine 2 theta d theta. So integrate theta, and this will be u sub. One half sine 2 theta by u sub. From 0 to pi over 4. Okay, let's double check to make sure we're doing everything okay. I can distribute now, and I get 2 theta minus sine 2 theta. Okay. So 2 times pi over 4 minus sine 2 times pi over 4 minus 2 times 0 minus sine of 2 times 0. So this portion again, you get 0, you get 0. Now this is sine of really 2 times pi over 4 is pi over 2. Sine of 90 degrees. Sine of, yeah. Looks like this is going to be sine of pi over 2. So sine of 90 degrees is 1. So we get pi over 2 minus 1 here. Yeah, I'm just doing some arithmetic in my head. So double check, ladies and gentlemen, that we did this the way it should be. See if we made any mistakes here. Just double checking. Yeah, there's a 4 here. There is a mistake. No, I think we're good. Okay, 2 theta. All right, it looks like it's okay to me. Anyway, here's my area. Area inside both curves. Now, here, there's a typo. There shouldn't be 3 curves here. Or should they? They might not. No, I think there might not be a typo. This is a 4-leaf rose. Okay. So I can tell this blue shape here, since we have an even, this is 4-leaf. So there's 4-leaf, and this is a circle in green. So let's kind of color coordinate that. This is the green curve, which is a circle. There's no error. And there's the blue curve. Now they say area inside both curves. That's here and here. As you can see, there is still some degree of symmetry here. So there is some symmetry. So I'm going to do something like this here. I'm going to say this to you. Yeah, we're going to find this area here. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . All right, let's see how this works here. Okay, so this is not as symmetric as people think, like in the last two questions here. So if I show you this line here, you don't really have the same kind of symmetry that you had before. I'm going to call this whole area here in red, this is going to be A1. So this is going to be the first time we do something interesting here with this. So here's what's going to happen. This A is double A1 because you do have symmetry, but it's looks like it's symmetric about the line, the angle theta being pi over 2, 90 degrees, or the y-axis. You know, you think of that as the y-axis, or the angle theta is 90 degrees. So what I know here is we use the right colors. This is my angle theta being 0 degrees. And this is that angle being 90 degrees. So I want to show you guys something here. We're going to have to find the point of intersection because I'm going to have two regions to determine here for the area here. Okay, so what I mean by that is here. The green portion goes from 0 to some theta. We don't know what this theta angle is. We don't know that point of intersection. We're going to find it. And in that portion, we touch the green curve. We touch the circle here, right here. And then from that angle theta to theta being 90 degrees, we're going to touch the blue curve. So what we'll be doing is finding this area in green and adding it with the area in blue, if you can see that there, because we're touching the curves at different locations once we find that point of intersection in red. So that's kind of what's happening with this. There's going to be some very interesting things here going on. So we have to find that angle theta. Now, if you said to me, are you saying A1 is the following? This is what I'm saying. That A1 is the area, I should say, in green. And that goes from the angle theta being 0 to some theta we haven't found. That's the green area. And we're going to call that, I'm going to label this in green. This is 1/2 r squared. We don't know what that is. You know, we can actually do this in green, I guess. I don't know. See what happens when you do this color stuff. All right. Integral from 0 to some theta, 1/2 r squared. Now, this will be plus. And I have to change that color. We need the area now here in blue. And it's touching the blue curve. And you go, okay, let's get blue. 0, or not 0. It's going to go from theta now. It's that same theta. We need to find that value to pi over 2 here. So we're going to go, this is our theta that we need. We don't know what it is yet. So we're going to go from theta is that angle to pi over 2 for the blue curve. This is area between curves now. And that will be 1/2 r squared d theta. And so this is how we're going to find that A1. And of course, the A1 area needs to be doubled. So we know the blue curve and we know the green curve. We need to know theta, though. So, I mean, I can put the blue curve in, which is sine 2 theta. So here, R is sine 2 theta. We know the blue curve. And then the green curve is sine theta. So this curve here will be just simply sine theta. Now, A1 then is simply 0 to theta, 1/2 sine squared theta d theta plus 1/2 sine squared 2 theta d theta. Because we just squared r. And that goes from that theta to the 90-degree angle, since we're sweeping here counterclockwise. So the question is, what is this theta? That's what we're going to need to find out. We know this one is 0 degrees. $90 degrees. And what is that theta value? That's what we're looking for. Now, in order to get theta, we have to set the curves equal to each other. So that means r equals r to get that theta, or we get sine 2 theta equals sine theta. So sine 2 theta equals sine theta. We're going to use an identity for sine 2 theta. We're going to use 2 sine theta cosine theta. And that's sine theta. We're going to subtract sine theta and factor out sine theta. We're going to solve this trig equation. So when you factor out that sine theta, you get 2 cosine theta minus 1 equals 0, which means two things. It means sine theta is 0. It means 2 cosine theta minus 1 is 0. And solving for cosine theta, we get 1/2. Now, sine theta is 0 means theta is 0, theta is pi, and theta is 2 pi. So the points of intersection happen at 0. They happen at pi. This is theta is pi, and they happen at theta is 2 pi. You may say, why am I focusing on quadrant 1? Well, we're using theta is 0 here. Increasing theta is 0. But these are the points of intersection that sine theta equals 0 give us. We need this theta in quadrant 1. We need the quadrant 1 theta. So quadrant 1 theta, we remember cosine theta equals 1/2. You know, cosine's positive in all students take calculus in quadrant 1 and quadrant 4. So the first cosine theta equals 1/2 implies theta will be pi over 3. All right, here's theta. Here's your right triangle. Definition of theta is going to be adjacent over hypotenuse. That's the square root of 3. And this means this will be, ladies and gentlemen, 60 degrees or pi over 3. This is how we got that. So the theta they're talking about is pi over 3. So that's this theta. Theta equals pi over 3. So we're going to go from touching the green curve from 0 to pi over 3. We touch this green portion right here. And then from pi over 3 to pi over 2 now, we touch the blue curve, this portion, for that angle. So now we just have to integrate with this pi over 3 here. So we know that angle being pi over 3. So this is going to be, let's change that. 0 to pi over 3, it's the green curve, right? Right up here from 0 to pi over 3. And then from pi over 3 to pi over 2, it's the blue curve. So I'm going to have a couple of half angle identities to use here and here, right? Or power reducing. Power reducing. I think what I'm going to do is I'm going to erase how we got the points of intersection. So I'm going to erase this points of intersection. It should be in the video. Just so we can see the integration. Just so we can see the substitution right here, the half angle identity here. Right, this is going to get replaced with 1/2. And I can put 1 minus, I think I prefer to do that, 1 minus cosine double theta. 1/2, 1 minus cosine 4 theta. Because you already have 2 theta. So if you double 2 theta, you get 4 theta. And then 1/2 times here, let's see what we get for A1. The integral 0 pi over 3. 1/2 times 1/2 is 1/4. 1 minus cosine 2 theta d theta plus the integral from pi over 3 to pi over 2. 1/2 times 1/2 is 1/4. 1 minus cosine 4 theta d theta. So ladies and gentlemen, you're going to have to do these actually separately, just so you know. Integral 0 pi over 3, we can say 1/4 minus 1/4 cosine 2 theta d theta plus integral pi over 3 pi over 2 1/4 minus 1/4, that's cosine 4 theta d theta. So let's do our integration. Now, if you want to change the colors here on this, you know, to say, well, to see this, I don't know. You don't have to. Here's what we're going to get. I'm going to integrate 1/4 theta. This is going to be u sub over here. This is also u sub. So be careful here. Look at that 2 theta. Look at that 4 theta. So kind of keep up with me on this. This is going to be 1/8 sine 2 theta, and that's from 0 to pi over 3, plus 1/4 theta minus 1/16 sine 4 theta, 0 to pi over 3. One-fourth pi over 3 minus 1/8 sine 2 times pi over 3 minus 1/4 times 0 minus 1/8 sine 2 times 0. And that's the first integral. Just to let you guys know, in orange. This whole thing is the orange. Let's do the next one. That's plus this green portion. So, plus 1/4 pi over 3 minus 1/16 sine 4 pi over 3 minus 1/4 times 0 minus 1/16 sine 4 times 0. And that's the green portion. So I would identify the easiest things to simplify, like this portion is 0, this portion is 0, 0, and 0. So here's what we get. Pi over 12 minus 1/8 sine of 2 pi over 3 plus pi over 12 minus 1/16 sine of 4 pi over 3. So if I combine my pi over 12, 1 pi over 12, 2 pi over 12, it looks like you'll get pi over 6 minus 1/8 sine 2 pi over 3 minus 1/16 sine 4 pi over 3. Okay. So we're going to need to know a couple of things here. Can't erase that. We need to know what sine of 2 pi over 3 will be. We didn't know right in here. We didn't know sine of what 4 pi over 3 will be. So we need to find sine 2 pi divided by 3. So we're going to have to deduce this. Let's think about this here. Okay. This angle here, in case people forgot how to do this, pi over 3 is 60 degrees. So this is sine of 120 degrees. Pi over 3 is 60. 60 times 4, that's sine of 240 degrees, right? So we need to know what those things are. Sine of 120, if you guys recall, is the square root of 3 over 2. So this portion, square root of 3 over 2. And sine of 240 is minus square root of 3 over 2. Okay, and now sometimes people will say, well, why is that? Well, pi over 3, if you remember, is 60 degrees. So we can take a 60, 60, 60, which reduces to the following triangle. Here's 60, here's 30, here's 90. 1, 2, square root of 3. Sine of 60, though, by definition, is opposite over hypotenuse. So that's going to be square root of 3 over 2. So I know sine 60 is square root of 3 over 2. And this is all students take calculus. So here's 60. Here's 120. And then 240, remember, is in quadrant 3. So this is going to adjust the signs. In quadrant 1 and quadrant 2, sine's positive, but when quadrant 3, sine is negative. So this is why you get a negative angle for the sine 240 and a positive angle for sine 120. So it's just going back and finding these values here. Anyway, trigonometry, the most important course you'll ever take in your life. 1/8 square root of 3 over 2 minus 1/16 times negative square root of 3 over 2. Pi over 6 minus, looks like it'll be square root of 3 over 16 plus the square root of 3 over 32. So multiply the bottom times 2 and the top times 2. Looks like it's pi over 6. Got to change that. Pi over 6, negative 2 plus 1, minus the square root of 3 over 32. So double check and remember something here. Remember that this is just A1. We're supposed to double it. This is just my A1. So I have to multiply this by 2, a factor of 2. So we get this area and this area inside both curves. So double it, multiply it by 2. So final answer is going to be, the area will be 2 times pi over 6 minus the square root of 3 over 32, which means the area is going to be pi over 3 minus the square root of 3 over 16. Anyway, double check, ladies and gentlemen, double check my work this late in the day. We're going to try this next one. So we want to see here if they ever change our instructions on this. Yeah, this is area inside both curves here. Okay, I believe this is still my instructions, area inside both curves. Now, what that really means for us, area inside both curves, is what you see here. This is still the area inside both curves scenario. Apologize for that. Hope that didn't happen for a long time. Anyway, area inside both curves. So the best thing I think to do here now would be just find the area of this portion here. This is my A1, and double it, so that the area will be double A1. Okay, and so the curve you see here now, this is a quadrant 1. Theta is 0. Rotate that to 90 degrees. Theta is pi over 2. And ladies and gentlemen, it's the purple curve. And the purple curve is r squared sine 2 theta. So if we just simply find this area and double it, we are done. So let's see what that means then. Area is going to be, I'm going to put it all together, double from 0 to pi over 2, 1/2 r squared sine, or 1/2 r squared theta. There's your d theta. We know r squared already. The purple curve is really sine 2 theta. So this purple curve here is sine 2 theta. So just replace that with a sine 2 theta. So pull out your constant, 2 times 1/2 integral 0 to pi over 2, really sine 2 theta d theta, which is 0 pi over 2 sine 2 theta d theta. Now integrate. Derivative of cosine is minus sine. So this is minus cosine 2 theta. But be careful, ladies and gentlemen. That's actually minus 1/2, because you're going to have to use u sub. And my u here is going to be 2 theta. So integrate this from 0 to pi over 2. Minus 1/2 cosine 2 times pi over 2 plus 1/2 cosine 2 times 0. So we get minus 1/2 cosine pi plus 1/2 cosine 0. Now cosine of 0, ladies and gentlemen, is 1, and cosine of pi is -1. So we get minus 1/2 times -1 plus 1/2, or 1/2 plus 1/2, which is 1. So the area here for this question, the whole gray region here, area is 1. So it looks like it's a 1/2 in each one. This is 1/2, and that's 1/2. Don't forget, we doubled it. So ladies and gentlemen, this is how we handle area inside two curves. What we'll look at later is area that lies inside the first curve, but outside the second curve. And that's going to be another video. So let's call it a day for that one, and we'll make the second one on another time. I hope you guys enjoyed.